Hello and welcome to a new video in a course on abstract algebra. In the previous video, we defined what groups are and we gave some basic examples of groups. In this video, I plan to cover slightly more advanced examples of groups. And I do understand that the level might be a little bit basic for these videos. However, I do believe that one should see proofs at the basic level before getting into harder proofs and harder examples. So in this video I plan to cover some more examples of groups, but these are important examples that will be showing up over and over again. However, I also plan to cover some important definitions that are related to groups, right? Such as the order and commutativity of group and so on. So let us start by going over these important examples that I have in mind. Before that, let me just remind you real quick of what a group is. So a group is you have a set, and in this set you know that this set is not empty, and in this set you have an identity element that satisfies the property E dot G, where dot is the operation. So this is the operation. The identity satisfies the property that E dot G is equal to G dot E is equal to G for every G in G. So in other words, applying the operation of the group to G, any element G and E gives you G back, right? So this is the setup, and we require the dot to be binary operation. So we require this to be a binary operation, and what this means is that we require G to be closed under that operation. And the next thing that we require is associativity of that operation. In other words, we require that taking A dot B dot C is the same as taking A dot B and then dot C. So applying the operation to three elements doesn't matter in what order you do that. So this is for every A, B, C in G. And the third property we require the existence of identity element that we just mentioned, and we denote it E. And the fourth property we require existence of inverses, and that is we require for every G in G that there exists an H in G such that G dot H is equals to H dot G is equal to the identity. So this is what we discussed in the last video, and we're now gonna give some examples give more examples of groups that satisfy give more examples of sets that satisfy these axioms, and thus they form a group, right? So the first example is what's so-called integers modulo n. And this example is very important because as we will see later, it's the typical example to think of when it comes to finite groups, right? We're gonna define what we mean by finite later. So let me just tell you what this group is, and let us prove that it is actually a group. Since we'll be going over the other example on a separate slide, let me just get rid of this. So let us prove that this is actually a group, right? But first of all, let me tell you what it is. So recall modulo n arithmetic. What does that mean? So m modulo n is equal to m take away all multiples of n. So let me just say it's m minus all multiples of n in M. So just as a quick reminder for you, what is, for example, what is 11 modulo 5? Well, this is equal to this is equal to 1 plus 10, and 10 is 2 times 5 modulo n. So so if we take away this multiple of excuse me, this is 5. If we take away this multiple of 5, we will be left with 1 modulo 5, right? So this is a quick reminder for you, and arithmetic operations modulo 5 is the same as arithmetic, the usual arithmetic operations over the integers, except that you reduce modulo n. So this is the definition of taking a number modulo n. So Zn is the set of integers modulo n. Now, when you take the set of, when you take all the integers and you reduce them modulo n, you will be left with the set 0, 1, 2 up to n minus 1, because all other elements will be like, we can take away multiples of n from them and we can reduce them back to this set. But notice none of these elements can be reduced back, can be reduced more, right? Because all of these elements are less than n, and thus they have no multiple of n in them, so we can't reduce them anymore. So this is the set of integers modulo n, right? And what we're gonna do is that we're gonna equip this set with the addition operation, and this addition operation, we're going to define it to be in this way. We're going to define a plus b to be a plus b modulo n. So let me just tell you what I mean here. So this is addition in z mod in z sub n, and this is addition in z, right? So this is the usual addition that you do for the integers. So this is how we're defining the addition. So the next thing we're gonna do is that we're gonna prove that. So here's the claim: z sub n with the addition is a group. So let us prove this real quick. So the first property we want to prove is closure under addition. So why is that the case? Well, because if you take any two, so this is a very important thing, right? So if you take any two numbers, so for every a comma b in Zn, so these will be numbers between, i.e. a and b will be between n minus 1 and 0. These will be integers between n minus 1 and 0. If you add these two, the way we're defining addition is that this is the same as or this is defined as a plus b modulo n, which means you're gonna take this, add this to whatever number it adds up to, and then reduce it modulo n. So perhaps let me just give you a small example here. So for example, if you take z sub 6, right? So this is the set of all numbers modulo 6. So this is 0, 1, 2, up 4, up to 5, right? So so for example, if you take 4 plus 5, the way we're defining addition modulo 6 is that this is the same as 4 plus 5 modulo 6, right? And 4 plus 5 modulo 6 is 9 modulo 6. But if you take away the multiples of 6 from 9, so 9 is 3 plus 6. So if you take away this 6, you'll be left with 3 modulo 6. So the reason I'm doing this example is to tell you that whatever two numbers we add from this set, even if it goes beyond the elements of the set, even if it becomes an element that's outside this set, when we reduce it modulo 6, we get it back to this set, which means that this set is closed. So this element is gonna be in Zn, right? So this set is closed under addition. I hope that this is clear. So the second property that we want to prove is associativity But I remind you, addition in z sub n is the same as addition in integers, except that we're taking modulo n, and modulo n respects the properties of this addition, and thus I'll leave it to you as an exercise to check associativity of this. Check that a plus b plus c is equal to a plus b plus c for every a, b, c in z sub n, right? I'll leave it to you as an exercise. Well, this is actually the proof, but just write things down so that you're confident with this. You're comfortable with this. So the next thing we want to show is the identity, the existence of an identity. Now, before I tell you what the identity is, here's one thing I want you to do when you do abstract algebra. When you do abstract algebra, I want you to think first of all of the obvious. So whenever you have a problem, think of the obvious before thinking hard, right? If the obvious works, then you're done, right? So do not think hard before thinking of the obvious. This is the big thing in abstract algebra. So please do that, right? So if I ask you now, what's the identity if the operation is plus, right? What's something that when added to any other thing, it gives you the thing that you started with? Well, that's 0, right? So when we're talking about addition, for example, if we were talking about multiplication, we would guess that it's 1, right? But here we're talking about addition, so our guess is that it's 0, right? So our guess is that e is 0, and we're gonna verify this. Well, is there a 0 in Zn? Well, of course there is, because remember, Zn is the set of 0, 1, 2 up to n minus 1. So if you take any other element, so for every a in z sub n, a plus 0, which is the element we're claiming, is equal to 0 plus a, so is equal to a plus 0 modulo n, right? So this is what we have, but this is the same as a modulo n, because this is the addition of in integers, and this is the same as 0 plus a modulo n, and this is the same as 0 plus a in Zn. So this is the addition of Zn. So which is the same as so this is also the same as a, because a is already between 0 and n minus 1. Because a is already between 0 and n minus 1, thus modulo n, it's going to be the same, right? For example, if you look here, if you take any of these numbers, like for example 5 modulo 6, it can't get smaller, right? It can't get reduced more, so there's going to be 5. 3 mod 6, it's 3, right? Alright, so the next property we want to check is what's so-called existence of inverses. Why do inverses exist? Again, here I want you to pause and think. I want you to think of the obvious. Like, let's start with an element in z sub n. So this is gonna be a number between 0 and n minus 1, right? So this is an element of z sub n. And the question is, what's the inverse of it? So we want an element which, when we add it to a from either side, we want to get the identity. But what's the identity here? Well, the identity is 0, so we want to get 0, right? And remember, this addition is happening modulo n, which means you're gonna add the numbers as integers and then you're gonna reduce them modulo n. So what element would you choose so that you get 0, right? So you might think that, let us try the obvious, let us try minus a, right? Let us try minus a. So though the addition of these as integers is equal to 0, and thus their addition modulo n is equal to 0, like minus a is not in Zn, right? Because if you is not yet if you don't reduce it modulo n. So if you look at for example in z sub 6, 3 is in here, but negative 3 is not in this set, right? So how would we handle this? Well, here's a trick that I wish that you keep track of this. if A is in Zn, then n minus A is in Zn. Okay, n minus A is in Zn, because if A is between n minus 1 and 0, you can subtract, you can first of all multiply by minus, and it's going to be minus A between it's negative, and between negative n plus 1, and then you can so this is going to be negative A, and then you're going to add n to this. Just a bit of digression here. You're going to add n to this. It's going to be n minus A between n and 1. And we may assume that A is strictly less than is strictly bigger than 0, because if A were 0, then its inverse is obvious. If A is 0, the inverse is just 0, right? Because 0 plus 0 is 0. So we may assume that it's strictly bigger than 0, and thus it's strictly less than 0 here. Thus this is strictly less than n, right? So n minus A is always in Zn. So n minus A is in Zn. But not only that, it's also that when you add these two, like when you add these, what's the answer? Well, this is going to be A plus n minus A modulo n, which is equal, the a's cancels, n modulo n. Now take away the n's from the n, well, what's left is 0, and thus this thing is the inverse of A. So this is a very important trick to keep in mind. The inverse of an element in Zn, if an element A is n minus A, right? Unless A is 0, in which case its inverse is just A itself. And this actually proves this. That's it. This proves that Zn with addition is actually a group. I hope that you keep track of these tricks. Okay, so the next important example we're gonna do is what's so-called the group of matrices. So here's a new example. We're gonna take M sub n, and this notation is very important because we're gonna be referring to it. So I hope that you keep track of this in your mind. So M sub n is gonna be the set of all n by n matrices. And some people put R to indicate that we're talking about real matrices. We're gonna assume this for granted, that we're talking about real matrices, okay? So let Mn be the set of all n by n matrices, right? What we're gonna do is that we're gonna equip this with the addition, and this addition of matrices, like the element-wise addition of matrices that you're familiar with from linear algebra. Like if you have a matrix A that's equal to Aij, and a matrix B that's equal to Bij, we're gonna define A plus B to be Aij plus Bij as this, right? As a matrix. So this is how we're defining the addition, and this Mn is an important notation that for you to keep in mind. It's the set of n by n matrices, and the claim is that Mn with the addition is a group. So this is an easy thing to check, because you know you're familiar with the linear algebra behind this, but perhaps let us do this real quick because this is important. So this is a proof. So first of all, let's do closure under addition. So why is it closed under addition? Well, of course it is. Let's call this the definition. So this is clear by the definition. Why is that? Well, it's because if you take any two matrices, you're adding these, you're still getting a matrix. Nothing changed. You take, right? So closure is evident. 2, we want associativity. I'll leave it to you as an exercise, and this is something that you must have seen in linear algebra, that matrix addition is associative. 3, the identity. back to the recommendation about what to do in in abstract algebra. So you want an identity, and we're talking about matrices, and we have the operation plus, right? So what's a matrix that you would like to think of, which when you add it to any other matrix, it gives you the original matrix back? Well, that's the zero matrix. Surprise, surprise. So let's take the zero matrix, and let's call it zero, big zero, to be the matrix with entries, with all entries are zero, right? So it's the matrix with all entries are zero, with all entries are zero, right? So the zeros everywhere. Okay. So if you add O to any matrix, so for every A in Mn, for every matrix A that's n by n, if you add 0 to A, it's the same as adding A to 0, and this is the same as let's say A is Aij. Well, the zero matrix plus any other matrix gives you the matrix back, right? So there isn't much here to say. So the fourth thing that we need to prove is the existence of inverses. So for every A in A in Mn, for every matrix A, we want to find an inverse to it. We want to find a matrix B. So we want B such that if we add A to B in either way, we want to get the identity. What's the identity here? It's this thing. It's the zero matrix. So so let's say A can be written as Aij. What would you take B to be? Well, again, you do the obvious. You take B to be the thing that you think of. Well, A plus B. Let's say B is Bij, and we're trying to figure out what the Bij's are. So this is Aij plus Bij, and we want to get the matrix 0 back. So this is what we want. So what would you take Bij's to be? Well, obviously you would take negative the Aij's because you want these to cancel out, right? So if you take Bij to be negative Aij for every Ij, this will give you the matrix. This will give you the matrix B equal to negative Aij's is equal to negative A. And this is what you would think of, right? To cancel the matrix A and get a zero matrix, you add negative A to it, right? So this completes the proof that this is actually a group. Alright, so the next thing we're gonna do is what's so-called the general linear group. So the general linear group is one of the very important examples of groups, and the reason, or one reason, is that it's gonna be the first typical example you're gonna think of when you're asked to find a non-abelian group. So we're gonna define this terminology later, but I'm just trying to throw some technical terms here. So the next group we're gonna be talking about is the general linear group, and the notation, or let me just tell you what it is. It's the set as a set. As a set, it's all the n by n invertible matrices. So GLN is all the n by n invertible matrices, and some people usually put R here to indicate that this is actually a set of real matrices. The entries are real, but we can ignore it because we'll be working with real matrices most of the time. So GLN, it's the set of real matrices A that are real matrices, and they are n by n matrices, such that we want the determinant of A not to be 0. So this is what the definition is. And the claim is that if you take GLN with the operation times, so this is the multiplication of matrices, then, or let me just say, is a group. So if you take the set of all invertible matrices and you take the operation to be multiplication of matrices in the way you know from linear algebra, then this forms a group. Now let me just just for sharpening your understanding of what a group is, let me just tell you the proof for GL2. So we're gonna proof GL2 is a group. So GL2, I remind you, it's the set of all 2 by 2 invertible matrices, i.e. those with determinant not equal to 0, or those where the inverse exists. And we're gonna take the operation to be multiplication, matrix multiplication. So let us prove this. So the first thing that we need to check, again as usual, we need to check that this operation is binary. So we need to check that this operation is binary, i.e. you want to check that this is a closed set under this operation, which means if you start with any matrix A and any matrix B that are in that set, i.e. they're invertible, and there are 2 by 2 invertible matrices, we want to prove that the resultant matrix, if we multiply these two, we want to prove that we're gonna still be in GL2. But what does it take for us to be for AB to still be in GL2? Well, it takes for it to be it has to be invertible, right? So I remind you here, the determinant of AB is equal to the determinant of A as the determinant of B. So this is from linear algebra, but if this is not 0 and this is not 0, then this whole thing is not 0, and thus the matrix AB is invertible. It should just means that AB is in GL2. And as a reminder from linear algebra, I want to remind you that the inverse of AB is actually B inverse times A inverse. So it's the product of the inverses, but in the reversed order. So the next thing that we need to check is associativity of matrix multiplication. But again, I take it for granted now that you guys have seen this in linear algebra. This is something also easy to check, so I'll leave it for you as an exercise. So the third thing that we need to check is what's so-called the existence of identity element. So before I tell you, well, it's in front of you, but before we say anything about this, let me remind you, please do the obvious, which means we're talking about matrix multiplication, and we want an element, we want a matrix such that when we multiply it with any other matrix, we get the other matrix back. And obviously the first thing to think of as a person who, as you guys, as people who studied linear algebra before, is the identity matrix, right? So you check, does the identity matrix work? Well, it turns out that it does. And you check this, well, let's take I to be the identity matrix 2 by 2, because we're talking about 2 by 2 matrices. And note here that this is in GL2 clearly, because the determinant of this is 1, which is not 0. And you check, well, A times I is equals to I times A, and is equal to A. And this is the definition of an identity of a group. And that's it. You just found it, right? It's the identity of a group is that, and that's it. So the next property that we need to check, or the next axiom that we need to check, is the existence of inverses. So we're gonna start, let A be in GL2, right? 2 by 2 invertible matrix. And what would an inverse be of that? Well, I remind you, in groups, or in the axiom of defining groups, the inverse is an element which, when we apply the operation from either side, we get the identity back, right? So we want an element B such that A dot B is equals to B dot A is equals to the identity, but the identity here is the identity matrix, so we want this to be I2, or the identity matrix. So what kind of B can you choose? Well, again, you think of the obvious from linear algebra, there is such a matrix that we know, which is called the inverse of A. And the reason we can talk of the inverse of A is because A is actually invertible. Well, take that as the inverse. Well, the inverse of A is thus the inverse of A from linear algebra as a matrix is actually the inverse of the element of this thing that we're trying to prove is a group, because it satisfies this property. And this actually completes the proof. This completes the proof that GL2 is a group. And I want you to adjust this proof so that it works for GLN as an exercise for you guys. And if you guys want to see a cleaner proof, here's a cleaner proof to look at. Anyways, so the second half of this lecture will be about some important definitions related to groups. So let us go over these real quick, and let us go over examples. So the first thing is the commutativity. What does it mean to say that a group is abelian? Well, a group is abelian. A group G is said to be abelian if we apply the operation in either side. We get the same thing. Like if we take AB, it's the same as taking BA, but this should happen for every element of the group. So let us take an example and a non-example of abelian groups. So as a quick reminder, we proved in a previous lecture that Z with the addition is a group, and this is the proof of it. And we also saw that like if we add, like you guys also know, like if you add integers in either order, it's the same, and thus this operation is commutative. And here I want to stress something. So when we say a group is abelian or commutative, this is relative to the operation. So please guys, when we say a group is abelian, this means that the operation we're taking, that we're equipping the set with, is actually commutative, right? So so if we were talking about R with multiplication, we will be talking about R being abelian with respect to the multiplication. So here R with star, taking away 0, R with the multiplication is abelian. So this is relative to the operation, right? So as another example, we also proved that if we take the real numbers and we take away 0 and we take the operation to be multiplication of real numbers, then this forms a group. But it also forms an abelian group, because if you multiply real numbers in either order, if you take a real number A and a real number B that are non-zero, right? If you multiply them in either order, A dot B is the same as B dot A, right? And thus the group is abelian. But again, it's important that we're talking about the operation multiplication, and thus we're asking whether or not the operation is commutative. So I remind you of two groups that we talked about. For example, the group GLN is, not abelian. And when we say is not abelian, it's when it is equipped with the multiplication operation. Let me just tell you the reason why GLN is not abelian. Well, the reason is clear. The reason can be like when you want to disprove something, you give a counter example, right? So we're disproving that it's abelian. So let us disprove it for GL2, okay? So if you take the matrix, for example, 1 1 0 0 and 1 0 0 0, for example, you multiply these out in this way, you get 1 0 0 0. And then if you multiply them in the other order, let's rewrite these and multiply them in the other order, you get 1 1 0 0. But these two are not the same, these are not equal, and thus this group GL2 is not abelian. I just given you a counter example, right? It's not abelian actually. Okay, so however, if we go back to the the other group that we discussed, which is the set of all matrices with the addition operation, then this is actually an abelian group, right? Because the addition is actually commutative. Well, why is that? Well, if you remember, this is how we're adding matrices. But adding matrices this way is the same as adding the entries in the other way, because the addition in real numbers is commutative. But this is the same as b plus a, and that's it. I mean, this proves that like this group is actually abelian, right? So so this is what we got. So the other definition on the list is the order of a group, and the next one is going to be the order of an element. So let us go over these real quick. So here's a definition. Given a group G with an identity E and multiplication dot and operation dot, the order of G, which we denote by O of G, is the number of elements of G. But I'm gonna put here number between quotations, because what it really is the cardinality of G. Because G can be infinite, right? For example, so we have two additional definitions. We have finite groups are groups of finite order, and we're going to give this as an example now, and infinite groups are groups of infinite order. So this is how we're defining the term infinite group. For example, if you take the integers with the addition, well, what's the cardinality of Z? Well, Z has infinitely many terms, so the order of Z is infinity, right? So so let us take an example of a finite group, right? So let's ignore, I don't want to introduce this notation now, we're going to introduce it later. So let's take Z6, though this is the same. So this is the integers modulo 6 with the addition. We just proved that Zn with the addition, Z sub n with the addition is actually a group, particularly Z sub 6 with the addition. The integer modulo 6 with addition is actually a group under addition. So Z6, it's the set of these elements, right? So the order of this group is 6, because how many elements does it have? Well, you count them. These are 6, right? And in general, so let me just say here, the order of Z6 is 6. And in general, the order of Z sub n is actually n, because remember, Z sub n is the set of 0, 1, 2, up to n minus 1. If you count these are actually n. Okay, so this is an example of a finite and an infinite group. It's a basic concept. Keep it in mind. Anyways, so the next thing. Alright, so the next thing we want to cover is what's so-called an order of an element. So let's do this. So here's the definition. Given a group G with identity E and operation dot, then let me just say let A, B, and G, the order of A, we're defining this, is the smallest positive integer such that if you apply the operation to n a's, like these are n A's, you get the identity back. Okay, so I stress a few things here. It's the smallest positive integer n, such that if you take the operation with n A's, if you take n A's and you take the operations between these, you get the identity of the group back. So I guess let's take an example to refine this real quick, right? But before that, let me just tell you, just as for the order of a group, we have like the order actually like separates the elements into two parts. If G is a group, let's say, if the order of A is less than infinity, we say A is of finite order, right? These are basic definitions. If the order of A is infinity, we say that A is of infinite order, right? So let's take an example of an element of a group that is of finite order. So if you take z, the integers modulo 12, z sub 12 with the addition. And so before I mention this, let me just tell you that the integers modulo n are the typical examples you should think of when you're asked to give an example of an abelian group or an example of a finite group, right? Because you see it's a finite and it's an abelian group. So this is something you should keep in mind. So z sub 12 with the addition. So our question is, what's the order of 4? So here's the general trick. So what you do in general is that you start by incrementing the order by 1, incrementing the integers by the number of terms you're taking by 1, and you see if you hit the identity or no. So here's what you do. Is 4 equal to the identity? What's the identity in Z12? Remember, it's the addition operation, and we agreed that this is the 0. Is 4 equal to 0? This is the identity. Because remember, we're trying to see the number of terms we need to get the identity back. Is 4 equal to 0? Well, no, because remember Z12, it has it's a set. It has distinct elements up to 11, right? So these are distinct. So no, and thus, so the order of 4 is not equal to 1, because here we took 1 4. Is 4 plus 4 equal to 0? We took 2 4s here. Well, 4 plus 4, remember the operation here is like you take the sum and then you reduce modulo 12, right? So is 4 plus 4 equal to 0? Well, 4 plus 4 is equal to 4 plus 4. If we take the operation modulo 12, it's going to be 8 modulo 12. But remember, taking modulo 12 means take away multiples of 12, but there is no multiple of 12 here, because we can't reduce the elements that are less than 12 anymore. So so this is not 0 actually, and thus no, the order of 4 is not 2. Is 4 plus 4 plus 4, taking 3 4s, equal to 0? Well, let's see. Well, 4 plus 4 plus 4 is equal to 4 plus 4 plus 4 modulo 12, and this is equal to 12 modulo 12. Take that 12 away, because we're taking modulo 12. This is 0, and thus yes, the order of 4 is what? Is 3, because we took 3 of these. Look at this for a cleaner solution. But I want to stress something, that the order is the smallest such integer, but like it doesn't mean that there aren't bigger integers, because bigger such integers, because if you take 4 6 times, you add 4 to itself 6 times, then this will give you 0 and this will give you 0. But the order is not 6, the order is 3, because the order is the smallest number of terms I need to get 0, right? So the order is not 6, it's the smallest number. And just to wrap up this video, because we mentioned infinite elements of infinite order, let me just tell you that the integers with addition is a group, and 1 is of infinite order. In other words, the order of 1 in Z is infinity. The order of any other element other than 0 is actually infinity, except that 0, if you take the order of 0, how many terms do I need to add 0 to itself to get 0 back? Well, one term, one time, right? So usually in any group, the order of the identity is 1, but but in this case, the order of any other element is infinity. So why is the order of 1 infinity? Well, because if you take 1 and add it to itself n times, so let's say n times, right? So what is this? This is n, but n is a number of times, so it's positive, so this is not 0. So this can never be 0. This will never be 0, and thus the order cannot be a number, because it doesn't matter how many times you add 1, you won't get 0 back. That's just not possible, right? So the order of 1 is infinity. So in the next video, we'll be covering what's so-called cyclic groups. So stay tuned for that.